speaker. All right, that's good. Hello. And so I don't see either of your videos on the Dropbox. So I'm just wondering, are you planning to present live or share video or live? All right, good. You're muted.
Yeah, so hi, Dr. Graf. Good afternoon.
Hey.
Hello, everyone. I, of course, planning to present live.
Okay, great. I guess your video audio works. That's good. We have a couple of minutes if you want to just share your screen, make sure that works. And then also make sure you have the timing, especially if you present live. All right, I can see it. Might want to try full screen, make sure it's not in presenter mode or anything like that. Okay, looks like we also have the fourth speaker, Maria Grilli. Is that right? Hello. Are you planning to present live or share video, play live?
Yes, I have got the registered, but I will do live.
Okay, perfect.
Okay.
Yeah, that's good. I was in some sessions before where there was only videos being played, and you know, this is better.
It's better live, I think. No, okay.
Yeah, I agree.
Okay.
So I'm glad.
Okay.
All right. Do we have the others? Do we have any of the other speakers yet? I think we're still missing the third talk. Third talk, fifth and sixth talk. All right, let's get started. Welcome everyone to this session on fabrication of low-dimensional nano and 2D materials. My name is Gerd Grau from York University in Toronto, Canada. We have 6 talks in this session, so we won't go all the way to the full allocated time, but we still try to stick on time with every talk. And it seems like most speakers want to present live, which is great. Although we don't have all the speakers yet. Hopefully they'll come soon. So let's get started with the first talk. And the first talk is presented by Swapnil Ambade from UMBC. And the title of the talk is Molecular Interactions between Ti3C2, Maxine, and Amine containing molecules in aqueous buffered solution. Please go ahead. You're still muted. Do we need to oh, there you go.
Yeah, I'm good. Hello and good morning, everyone. Thank you, Dr. Grau, for your introduction. I'm Swapnil Ambade from Rosenzweig Group, UMBC. First of all, I would like to thank all the organizers for giving us an opportunity to present our work on molecular interactions between Ti3C2 Maxine and amine-containing molecules in aqueous buffered solutions. We heard a lot of interesting talks on Maxines yesterday, and from all these talks and all these available interesting reflections on Maxines, what we understand is that Maxines are transition metal carbides, nitrides, and carbonitrides that are obtained from a ceramic material called as max phase, where M stands for transition metals like titanium, vanadium, niobium, molybdenum, etc. A is typically aluminum and silicon, and X is carbon and nitrogen. So Maxine is just not one material with 3 different configurations in general from M2X, M3X2, and M4X3. It's a pretty vast family of materials with some 30 Maxines known so far and 80 max phases already reported. Well, if you look at this particular diagram here, it tells us the story of Maxines in the last 10 years. So over the decade, since the discovery of this interesting material Maxines by Professor Yuri Gogetz's group at Drexel, we see Maxines making good impact in the areas of energy, especially supercapacities and batteries, catalysis, electronics. And it's quite encouraging to see that Maxines are now finding quite an interest in the areas of biomedical science and also environmental science. Well, undoubtedly, Maxines are quite emerging 2-dimensional materials for future energy conversion and storage applications. Now, because these are new materials, and that's a pretty huge family of materials, in fact, just little is known about their impact on exposure to the environment because they're not been exposed to the environment yet. So basically, our aim is to study the biological properties of Maxines and understand the impact when they're exposed to the environment. Now, this is important because Maxines are eventually going to be used in many other applications, say something like water purification. Now, in this particular application, a lot of elements would be adsorbed when they would pass through Maxine layers, and we need to know what these adsorptions are, and if these adsorptions make any impact on the surface of Maxines. Then knowing what impact these interactions make on the surface of Maxines will also help us to protect the surfaces of Maxines in future so that Maxines can be used effectively for various applications. So basically, the starting point to all these studies in biological science is first to understand how vaccines would behave in a very basic or a very fundamental biological media, such as biological buffers. So I will talk about our preliminary understanding of how vaccines behave in different biological buffers. So we synthesize our vaccines using non-18 processor etching using a combination of hydrofluoric acid and hydrochloric acid to get these multi-layered vaccines. So these multi-layered vaccines are intercalated using lithium chloride to get these delaminated vaccines, which are more like monolayers of vaccines. So these delaminated vaccines can be stored in the form of vaccine inks, or we can also make vaccine films. In our case, we can achieve conductivity close to 18 to 20,000 Siemens per centimeter. When vaccines are formed, we know, we confirm this using this X diffraction, particularly the disappearance of peak around 39 degrees here tells us that aluminum has completely stripped off from the max phase in the vaccine, and the shift to lower angles of the 002 peak, and with the broadening of this peak tells us vaccines are delaminated or they exfoliated. So this is a typical visible spectrum of our vaccines. Vaccines absorb in two different regions. One is this visible region, which tells us about the delamination of vaccine. And the absorbance around UV region gives us information about the flake size, shape, and surface terminations. Now, as far as buffers are concerned, there are many different types of buffers, but two interesting buffers that are zwitterionic in nature, like MOPS and HIPS. MOPS is like this comes with the morpholin ring, and HIPS is the buffer with this piperazinic ring. These buffers are pretty common, and they have a pH range of 6.5 to 7.9, and HIPS has a pH range of 6.8 to 8.2, whereas this pKa values are 7.28 and 7.5. So HIPS particularly is also called as a physiological buffer because this mimics living system very closely. So for MOPS, the structure of MOPS is you have this morpholin ring and you have a sulfonic acid group here. So when we have our vaccines in MOPS buffer, what we see is the absorbance around this region goes down, telling us that the MOPS molecule actually decorate on the surface of vaccine. Well, also in case of HIPS, here we have a slightly different structure where we have a piperazine ring and the head group of sulfonic acid and a tail group of hydroxyethyl group here. So in this case, what happens is when we have vaccines in this HIPS buffer, the absorbance around this region goes down drastically, but there is no aggregation. It tells us that we see greater interactions when HIPS when vaccines interact with HIPS molecule. This is because of this huge deposition of these HIPS molecules over the surface of vaccines. Well, typically what happens is these buffers tend to intercalate through the surfaces of vaccines, and this we understand from the low angle shifts in the 002 peak in case of both the buffers. And also, we see that the full width of half maxima actually changes, telling us that there's some sort of stress and relaxation going on. And this is related to the structure of, this is quite correlated to the structure of these buffer molecules used. Now, our preliminary understanding is that when we try to watch these buffers back to and put them back into DI water, these peaks actually retain their positions, telling us that this is perhaps a reversible process. But that's not the case because we see some sort of picturing that's taken place even after it is washed. And similarly, it's also the case in case of MOPS buffer. So we believe this is a case of partial reversibility. and not the complete reversibility. And this is also evident from different azimuthal angles that we calculate here using this 2D exciting. We see that when we wash hips, the FWHM changes from 29.8 to 17.7, which tells us that there is this considerable amount of relaxation, but it doesn't come closer to the normal value of 21.6 in maxims. Now, there's one very interesting role that these terminal groups have on these buffer molecules have. So if you have hips where you have these two terminal groups, in this case, we see with high stability, there is no aggregation in this case. But when we have a molecule that does not have the sulfonic acid group, in this case, we see this peak going down drastically, but this is still moderately stable. It doesn't really aggregate. Now, in case of a molecule that does not have any of these groups, it actually tries to destroy the structure of maxine, leading to whole aggregation in this case. Now, one effect that we see here is our maxines are pretty stable in DI water. They do not oxidize. In case of hips, we see some sort of oxidation because we detect this TiO to be related. This is related to anatase TiO2, and we see that there is some partial oxidation here. Now, in case when we don't have the sulfonic acid group, there is no aggregation, but there is high oxidation here. And when we don't have any of these two groups present here, there's aggregation as well as very high oxidation. So this is the zeta potential of maxines in water, hips, and these all these molecules with different terminal groups and not having these terminal groups. And we see these differences because this tells us maxines interact in different media here. This is the electrical conductivity data. The conductivity drops down all the way from 20,000 to close to 4,000 or 5,000 for these molecules. And for piperazine, where it oxidizes very heavily, it's in some 100 Siemens per centimeter. Well, to summarize my talk, maxines, they interact with both these zwitterionic buffers, hips, and MOPs. And however, we see greater interactions with hips and buffer. Primarily, what these buffers do is they tend to intercalate through the layers of maxines. Then these interactions are partially reversible, and we're trying to investigate. The reversibility mechanism here, and we're also trying to investigate what sort of interactions these are using XPS studies, and we're also doing these DFT studies to understand these interactions better. So biological buffers, of course, have a striking impact on the conductivity of maxine sheets. So there are lots of people here, collaborators to thank. Very grateful to Professor Yuri Gogotsi and his group, especially Dr. Chris Schuck in his group for supplying us with max phase and those very interesting discussions, tireless discussions on sharing their knowledge on maxines with us. Then we are supported by the NSF Center for Sustainable Nanotechnology. Here, a very enthusiastic group, and all the participating PIs in NSF CSN who are also a part of our maxine collaboration. Then this is the picture of us during the new normal.
Please come to an end. That's you're a little over. So.
Okay. Thank you very much. Thank you for your attention.
All right. I guess you were almost at the end, but all right. Thank you for this very interesting talk. Unfortunately, we don't have time for questions. Maybe at the end of the session, if someone has a question for the speaker. So let's move on to the next talk then. All right, thank you. So the next speaker who's also going to present live is Balázs Danabalan from the Italian Institute of Technology. Please go ahead and share your screen. And the talk is entitled 2D perovskites for color tunable light emission. And there we are. Please go ahead.
Okay, can you hear me?
Yep, we can hear you. It's not full screen yet, though.
Yeah, now is it okay?
Okay, perfect.
Okay, yeah. Thank you very much for the introduction. I'm Balaji Dhanabalan. I'm the postdoc fellow at Italian Institute of Technology, Genova in Italy. Today I'll be talking about the 2D layer perovskite materials for the color tunable light emission. Before going into the key results, I would like to give a brief introduction about these metal halide perovskites. These perovskites are the semiconducting material with the general formula AMX3, where this M is the divalent metal, which coordinates with 6 halogens to form the octahedrons. And these octahedrons will be connected in all the 3 directions, and the void created by these octahedrons will accommodate the acyclic smaller cation like CCM. It can be either inorganic or the organic like CCM or methylammonium or formamidinium. These materials have been proven, have found applications in many different fields. For example, in solar cells, which has achieved power conversion efficiency of 25%, close to 25%, or also in the light emitting application, or also in flexoelectronics, many different applications. Yeah, even though these materials have been exploited in different for the different applications, the organic chemists wanted to include the organic part into these materials, and they want to bring new properties from this. The one possible way is to sweep this acid cation, and in the space created by these octahedrons can accommodate the organic molecules. Within that organic, but in general, the organic molecules are very long. But we have the constraint of this smaller space, so we have to do something. In that way, if they are incorporating the longer molecules, these octahedrons will not be connected in all the 3 directions. It will be connected only in 2 directions. Because of in the 3rd direction, these organic molecules will be like separating these sheets. So these materials are called the 2D organic inorganic layer metal halides, metal halide perovskites. And I have been working on these materials, and these materials have been found applications in different fields. Like we can tune the dimensionality so that we can tune the exciton binding energies, because it shows the quantum and the dielectric confinement, and also it found application in photovoltaics and the light emitting applications. By choosing properly the organic molecules, it also found application in spintronics. By introducing the chiral molecule into the system, that brings the chirality into these materials, and we can use it for the chiral applications. These are the different applications. Apart from that, it also found applications in ferroelectricity and the flexoelectricity. There are so many properties we can probe by playing with the organic molecules in this. These materials have been known for last decade. And there are so many synthesis procedures, and we found a procedure which is very simple for making this material. For example, we were just dissolving this lead bromide and the hydrobromic acid in acetone. And after this step, we just inject the amine, which acts as a spacer cation. Typically, at that time when I was working in 2019, the typical molecules were the butylammonium, decylammonium, which belongs to the aliphatic chain group, and or the phenylethylammonium or the phenethylammonium, which belongs to the phenyl ring group. And immediately after adding these amines into the system, as you see in the video here, it immediately creates a crystal. And after after the formation of the crystal, you can just take this crystal into the filter paper, and you can just try it for the further applications. These crystals, the SEA image, are showing the platelet-like morphology with the several microns in the lateral size and the thickness. It is very variable thickness. You can also reduce this thickness by mechanical exfoliation. And if you see the closer look, you can see the formation of these layers, like other 2D materials. This also shows the layer structure. But all these materials, irrespective of the organic molecule what we use, all these materials were showing the deep blue emission. And we were wondering, what is the way to change this emission? One possible way is to incorporate the functional molecules in the bonding group, so that these octahedrons will be distorted. That can change the band structure of the crystal, the band structure of the material, and that can bring the new emission properties. With this in mind, we were working on three different molecules, and with the two different molecular descriptors. One is the bonding group, and another is the alkyl chain. For the moment, we were keeping the alkyl chain constant, and we were working only with the bonding groups, different bonding groups. This the type 1 molecules are the primary ammonia molecules, which has 3 hydrogen for the bonding with the inorganic network. This we call it as the type 1. In the type 2 molecule, this is also the primary ammonium, but additionally, it has the additional methyl group, which has to be bond with the inorganic network. In the type 3, we chose the secondary ammonia molecules. It has only 2 hydrogen for the bonding with the inorganic network, and it has a methyl group which has to be incorporated within the void created by the octahedrons. As I told, we were keeping the alkyl chain constant for the moment, and we wanted to study only the binding groups. When these molecules has to be incorporated into the between the octahedrons, it will create the distortions between these bond length, and it can change different properties, and it can also change the electronic structure so that it will give different optical properties. With that in aim, we were studying all these 3 type molecules. In the type 1, which is the typical primary amine, as I was explaining before, it was showing the deep blue emission, which was not surprising, and we were expecting the same. And when we go from the type 1 to type 2, it was very interesting. Like when we just we observe the warm white light emission, and more interesting is when we go from the type 2 to type 3, which was showing the pure white light emission, which is very difficult to achieve from the single material. So just by changing the bonding group, which makes the bonding with the inorganic network, we can change the optical properties of this material. And we were wondering why, what makes this material with different optical properties. These are the CIE coordinates. We can go from type 1 to type 2 to type 3. We go from the deep blue to warm white light to the pure white light emission. And we were wondering why these materials are showing different optical properties, depends on the bonding group. So we did the theoretical modeling, DFT modeling on these materials, the type 1, which was showing the typical structure, and there was not much distortion in the octahedrons. When we go from the type 1 to type 2, it was showing the external distortion. That means the bond length from one lead to the other lead, it was changing, and it was creating the distortion in that, because it has to accommodate the additional methyl group within this octahedron. That's why it creates a distortion externally. An interesting thing is the one which was showing the pure white light emission. It has, that is a secondary amine. It has to accommodate the methyl group, and also it has only 2 hydrogens for the bonding, which was creating the internal distortion. That means the octahedron, within the octahedron, the bond length between the lead and bromide was changing. Because of that, the electronic structure was changing. That was creating the broadband emission. Typically, these broadband emissions are due to the self-trapped excitons, and these self-trapped excitons in general are due to the phonon vibrations. To study those phonon vibrations, we also did the Raman analysis on these materials, and we found different modes from going from type 1 to type 3. Still, we are analyzing these results. Still, we need to interpret more on this, and still we are working on this. So maybe we will come up with a nice correlation between the phonon modes with the self-trapped excitons. So with that, I would like to conclude. We were able to produce a layer perovskite material with a simple synthesis technique, which was showing the deep blue emission. By playing with the organic cations, we were also able to tune these optical properties from deep blue white light emission to the warm white light and to the pure white light emission. That was due to the distortion created by these organic molecules. And we also study these materials under the Raman spectroscopies to study the optical, to study the vibrational modes, which paves us the path to study the STE mechanism. Moving forward, of course, we were mostly working on the lead toxicity, so we have to address these lead toxicity issues. And in general, these 2D perovskites are in the out of plane due to the organic molecules, which brings, in fact, the stability, but it also hinders the out of plane transport properties. So we have to find some molecule which also brings the conductivity. So that would be a nice way to way to work on this material to promote the conductivity of this one, and the organic, as I was telling, the role of organic cations with different mechanical properties also, which can bring the mechanical properties into this, and the flexoelectrical and ferroelectric properties can also prove from these materials. And it also found application in photocatalysis, and we can use this layer perovskite material with other 2D materials to prove new properties from these things. And I would like to acknowledge all these people, especially my supervisors, Professor Roman Krani and Dr. Milena P. Archinagas, and also Professor Librotamanna, for giving me opportunity to work in this field, and also giving me the position, and also all these collaborators and the technicians and other administrative officers from my institute. And thank you very much for your kind attention, and I'm ready to take the questions. I hope I understand.
Great, thank you. Thank you for this interesting talk. Again, we're out of time, so let's postpone questions until later in the session. If I'm not sure if all the speakers are here, if you have all the talks, or otherwise after all the talks are done.
Yeah, sure. Thank you.
All right, thank you. So the next talk, I'm going to play the video. So let me share my screen. Okay, it should. Hang on. All right, there we are. Okay. Let me. Okay. So the next talk is by Nishay Isak from TU Ilmenau in Germany, and the title of the talk is Fabricating Three-Dimensional Self-Aligning Nanoparticle-Based Structures as Gas Sensor Array. All right, I think I need to share my audio as well, right? I don't think I've done that yet, so let me make sure. There we go. All right.
A very warm welcome to all viewers of this presentation on fabricating three-dimensional structures to be used as a gas sensor array. My name is Nishay Isaac, and I am a PhD student at Technical University of Ilmenau in the field of nanotechnology. Starting with motivation for this research, we need to develop gas sensors which are low cost, robust, miniature, and efficient in their energy usage, because they need to be used in air quality monitoring, wireless sensing networks, and smart buildings. One of the ways of making this work is with a bottom-up process called gas phase electrodeposition. This process requires three basic steps. The first step is generation. When you pass a gas between two metal electrodes which are at a certain distance from each other and induce a plasma in this region, you get a spark discharge, and based on this a soup of ions are created. There are three components to it. There are the gas ions, there is the charged metal particles, and there are the electrons, of course. Once the generation phase is ongoing, the next phase is transition, where the soup is transiting from the generation region towards the substrate, where we're going to collect these particles. The substrate is a conducting plate which is negatively charged, and a patterned photoresist on top of it. When the gas ions, which have a higher mobility, they come onto the photoresist, they start deflecting the charged metal particles into the openings, and as a result of this, nanostructures can grow out of these openings on the photoresist. We did some finite element method simulations for this to understand this increase in electric potential of the photoresist, and what we see is that the curve becomes sharper as the potential increases. And when we make some electron microscope images for such depositions, we see that the structures are following this focus effect of these openings. We call this the nearest neighbor interactions, because with the effect of these nearest neighbors, we can start growing such bridging structures. Instead of having one material, what we can also do is have a Pyrex glass substrate, for instance, which is non-conducting, and have domains of a metal, for instance gold here, which are completely independent of each other. And when we start changing the source of our nanoparticles in a sequential manner, what we can do is we can decorate the surface with 2 or 3 or 4 different material bridges next to each other. As we see here, that the first bridge, which is red in color, is constructed already, and the second set of bridges, which are green in color, are being formed. We make some electron microscope images of these steps, and we clearly see that these bridges can grow out of these openings which have access to the gold domains and form bridges. And we can do this over a larger area, and in a span of about 150 seconds, we can grow over 1,000 bridges of different materials next to each other, forming a sensor array. Continuing this further, looking at the overview picture of our chip, what we see is that in a sequential manner, we are growing platinum, then nickel oxide, and then gold bridges next to each other, which are separated by a distance of 5 microns between adjacent bridges. The idea is that we make this three-dimensional structure as a sensor, and this chip, which is the sensing chip, we make it into a plug and play device. So I would play an animation here to make you understand how this is working. So we have our sensor chip, which is placed inside a chamber, and from the lid we have the electrical connections going out. The electrical connections on the pads of the chips are made with pogo pin electrodes, and the electrical connections coming out from the tip are connected to an external circuit, which provides the electrical bias for making resistance measurements. Another animation to show what is happening on the surface. So we have background gas nitrogen and target gas ammonia, which we are sensing. And as it is moving, the platinum bridges, they start interacting with ammonia molecules, which get adsorbed onto the surface. Not only does it get adsorbed onto the surface, there are some ammonia molecules which are also getting adsorbed onto the nickel oxide surface. As a result, the sensing is done by primarily platinum bridges, but there is some cross sensitivity on the nickel oxide bridges as well. There is no interaction between the molecules and the gold bridges. As a result, no change in resistance can be seen. So we see that there are 3 different bridges on our substrate. In our experiments, we made an in-house LabVIEW program which can plot all these changes in resistance in real time for 3 different materials and for different concentrations, because this LabVIEW program is also connected to a dilution system. So for ammonia gas, for instance, we make in real time a plot where 3 different concentrations of ammonia gas is taken in nitrogen, and a real-time plot for relative change in resistance is plotted, and this relative change is defined as the sensitivity of our sensors. Not only for ammonia, but we do testing for other gases. For instance, for carbon monoxide, we saw that nickel oxide is the most sensitive bridge, and for hydrogen sulfide, gold bridges are the ones which were giving the best performance. Since we see that there is also an increase in resistance for other bridges, which means that there is a certain amount of cross sensitivity, what is possible is that we can extract the data out of these graphs and make use of neural networks or a pattern recognition software and follow the same principle which is for e-noses and use them to identify which gases are available in the environment. Coming towards the end of the presentation, there are certain messages which we can extract out of this presentation, out of this research. So the first point is that we made a programmable approach towards deposition of structures. It's a combinatorial approach because you can have multiple materials on the micro scale placed on a substrate where we want them to be. It's a bottom-up process, which means you start from nanoparticles and you are growing only in places where the openings are present on the photoresist, which means that this is a more material efficient method as compared to a traditional microtechnology method, for instance, liftoff. We showed nearest neighbor interaction. We made some simulations to understand and show how these self-aligned structures are growing and forming interconnect-like structures, for instance, bridges. The gas sensors which we showed, they operate at room temperature and they are low power, so their power consumption is about 50 microwatts, which is very much in tune with what is shown in literature for low power sensing. And last but not the least, this process allows for depositing multiple materials on the same chip, which means that we are working towards lab on a chip concept, which is quite interesting for our future research. I would like to put forward some references from which I've used the results in this presentation. In the recent past, we've been working extensively on gas phase electrodeposition, trying to understand its basics, and these are the some of the papers which we could publish from this work. I would like to thank our funding agencies, so the Deutsche Forschungsgemeinschaft and Carl Zeiss Stiftung, which continuously funds our work. In the past, we've also been funded by National Science Foundation from the US. I also provide to you the contact details for our department in case someone is interested. We are very much open to collaborations and trying to explain more our side or learn more from your ideas. A small photograph of our group. We made a hiking trip last year, quite interesting, to some places around our university. Last but not the least, I thank you all for your attention. Thank you.
All right, thank you for this interesting talk. Again, we're still a little behind in our schedule, so let's again postpone questions until later in the session and move on to the next talk, which will be presented live by Maria Grilli from ENEA in Italy. And the title of the talk is Experimental Demonstration of Absorption Enhancement of Single Layer Graphene in Optical Resonant Cavities.
Thank you, Dr. Grau. Can you see my screen?
Yep, I can see it. It's not full screen yet.
Not full mode. Yes. Okay. Okay, so I will start. Thanks again for the introduction. I will tell you about the demonstration of experimental absorption enhancement of graphene layers inside optical cavities. This work has been carried out at INEA, that is the Italian National Agency for New Technologies, Energy and Sustainable Economic Development at Casaccia Research Center in Rome, Italy. We know that graphene and other graphene-like materials are emerging candidates for several optoelectronic and photonic devices, such as optical modulators, switching, in computing as photodetectors in a vast range of wavelengths. Unfortunately, graphene absorption is quite low for such application. In a single layer form, graphene absorbs only 2.3% of the incoming radiation, and therefore its absorption should be enhanced. That is achieved generally by patterning graphene by electron beam or ion beam lithography, or coupling graphene with photonic crystals, metamaterials, plasmonic materials. And recently, the absorption in unpatterned and undoped graphene was simulated by using an optical filter. This is a recent work where it is shown the absorption, simulated absorption, as we can see here, maximum 50% in a multi-layer stack in a Fabry-Perot filter as a function of the number of layers of the cavity and as a function of the layer material, which are defined by the refractive index ratio. The outline of my talk is the following. I will tell you about the simulation of graphene layers in 3 different kind of filters: a symmetric Fabry-Perot, an asymmetric Fabry-Perot, and an asymmetric reflective Fabry-Perot, giving some insight about the radio frequency sputtering of the filters, about the graphene preparation and transfer, about the measurement of graphene absorption inside the Fabry-Perot, giving some conclusion and remarks. This is the first structure that we have investigated. This is a symmetric Fabry-Perot. I remind you that it consists of 2 reflecting mirror, separated by an optical cavity. If we insert graphene in the cavity where the electric field is maximum, we can have a higher enhancement of the absorption. As we can see, the light hits graphene several times. Therefore, the absorption of graphene is very highly enhanced, and the absorption is proportional of the number of reflection, which is proportional to the reflectance of the 2 mirrors. And in all the filters that we have simulated and also fabricated, we have used as the high index material, refractive index material, silicon, as the low refractive index material, CO2. The refractive index ratio is about 2.4, depending on the wavelength, and we have investigated filters in the wavelength range near infrared and mid-infrared. We have simulated the transmittance and reflectance by COMSOL multiphysics using the electromagnetic wave module and inferring the absorption by this formula, and the optical properties of graphene are expressed by these formulas. This is the first result of our simulation. We have seen that for a single layer graphene inserting in the optical cavity, the simulated absorption is about 40%, in perfect agreement with results of simulation, also reported by other authors. We have then switched to the sputtering process. We have grown our Fabry-Perot filter by radio frequency sputtering, starting from a 6-inch silicon target. We have grown silicon layers in argon atmosphere, CO2 layers in argon plus oxygen atmosphere, at a radio frequency power of 200 watts, high working pressure. Nevertheless, in our first experiment, we observed a damage in our graphene layers, and we could avoid graphene layers damage by increasing the sputtering pressure up to 5×10⁻² millibar, decreasing the radio frequency power to 50 watts, and further protecting graphene by a thin magnesium fluoride layer grown by thermal evaporation. Doing this does not compromise at all the optical properties of the cavity, being the refractive index of magnesium fluoride very close to the one of CO2 at the wavelengths that we have considered as central wavelength of the Fabry-Perot. This is the graphene grow, the Raman, these are 2 Raman spectra of our graphene that we grow by CVD on large area from ethanol. And as we can see, our graphene is quite good, having a very low defective band. And this is the fabrication process that we use for embedding graphene inside the filter. First, we have deposited by radio frequency sputtering the bottom mirror of the Fabry-Perot. In a separate chamber, we have grown graphene by CVD. We have transferred graphene on the top of the bottom mirror by using cyclododecane. We have done a mild heating treatment, evaporated the thin magnesium fluoride overlayer, and deposited on top of the magnesium fluoride the top mirror of the Fabry-Perot. In doing the first the sputtering of the first layer close to magnesium fluoride, therefore close to graphene, we have used the mild sputtering condition. That means a low sputtering power and high sputtering pressure. And we can see from this Raman spectrum that the graphene quality is preserved, the single layer of graphene is preserved, only we have an enhancement on the D band after the sputtering process of CO2, while After a magnesium evaporation, graphene, the band remains unchanged. Also, this slide shows that transmittance spectra in the UV, showing that absorption peak of graphene in the UV is preserved also after the sputtering process. I've not shown here, but we have also measured the resistivity of graphene that remains unchanged after the whole process. And this is the first experimental result. In these curves, we compare the simulated and experimental transmittance, reflection, and absorption curves, and we show a very good accordance between the theory and the experimental value. We have repeated the experiment with using two-layer graphene. In this case, a single-layer graphene was transferred twice inside the Fabry-Perot, and we observed an increase in the absorption and also an increase in the bandwidth. This is the case of 5-layer graphene. We can see both theoretically and experimentally a decrease in the absorption. This is due to the fact that 5 layers graphene absorb higher radiation with respect to the single layer, therefore reduces the reflection of radiation inside the cavity. We have done the measurement by spectrophotometric of tear measurement according to the wavelengths by using certified mirrors in the different wavelengths. And to further enhance graphene absorption, we have increased the number of the layers in the bottom mirror. This is the case of the electric field distribution inside the filter. We can see a double peak, meaning that we can put graphene in 2 different positions, having the maximum absorption enhancement. And we have done the simulation, putting graphene in where the electric field is maximum. We have these 2 positions close to the top mirror, close to the bottom mirror. And we have also simulated the graphene absorption in the middle of the cavity where the electric field is almost 0, having only 8% of absorption. And we have simulated also the insertion of 2 layers of graphene, one here in the top mirror, one in the bottom mirror, and having a higher bandwidth and a higher absorption of about 47%. We have done the experiment in the easiest fabrication condition, obtaining 50% of absorption, also in this case in very good agreement with the theory. We have further increased the reflectance of the bottom mirror by further increase the reflectance of the bottom mirror. Here we have got only 1 position. We can see the experimental results here showing 84% of absorption against the 87% that we obtained by simulation. We have also done the simulation of the absorption as a function of the wavelength and the incident angles, and also as a function of the polarization of the light. Also, we have studied how the bandwidth changes with the incident angle and how we can change the wavelength without having a very strong decrease in the absorption peak. And as a conclusion, I have demonstrated that a high absorption can be obtained in imparting graphene in optical cavities, and that absorption increases by using asymmetric Fabry-Perot filters up to 84% that we demonstrated experimentally, and as far as we know, this is the first experimental proof of this concept. We will change the central wavelength to the visible, changing also the material and also the substrate, and enlarge the bandwidth by increasing the number of cavities or the number of graphene layers. And I acknowledge the collaboration of my colleagues, especially Abedin Nemakpour, that made 2 stages at INEA laboratories funded by the Ministry of Science, Research and Technology of the Republic of Iran and by ICTP in Trieste, Italy. And I thank you for your attention.
All right. Thank you for this interesting talk. We're still behind, but I think we don't have the next speaker. Is that right? And I don't have the video recording. Is the next speaker here? Because if not, then we have 5 minutes now where we can finally get to some questions.
A little bit, okay. But we can, okay. No problem.
For you or for any of the speakers?
Yeah.
I guess we
No
didn't have
problem.
time for any of the questions. So if anyone has any questions for any of the speakers, either raise your hand or, as long as not everyone talks over each other, you can just unmute yourself and ask your question. Actually, I have a question for the first speaker. There was a talk on the vaccines and the buffers. Swapnil, I think, is she here? No, I guess I can ask my question another time then. Does anyone have any questions? Well, let me make sure. I think the last talk, the speaker's also not here. Is that correct? But I have the video, so I can play the video. Okay, any questions? Anyone? Okay, I also have a question then, if no one else has any questions. I have a question on which talk was it? Oh yeah, about the self-aligned nanoparticle based sensors. Nishay Isaac, I guess. And my question is, I guess you're here, is that right? Yes, you're here. All right. Well, I just have a question, and so it's very interesting how you grow these bridges. And it's a bottom-up approach, which can sometimes be difficult to control. Okay, let me see if I can unmute you, or if maybe she can help with that. So I can only click ask to.
Yeah, thank you. Now I'm unmuted.
There you are. All right, great. So I'm just wondering, because it's a bottom-up approach, and sometimes that can be difficult to control. So what is sort of the yield that you get and the variability with these bridges?
Sorry, come again. What was the first one before variability?
Yeah, yield, the fabrication yield.
Okay, the yield. I see. So first of all, coming to your second question about variability. So the morphology is really dependent on a lot of parameters. So for instance, every material, so we are going different materials. So the material, this is more material dependent. For instance, nickel, if we start with nickel, but we get nickel oxide. So if you work in an environment where the gas is, let's say Fermier gas, which is 5% hydrogen in nitrogen. So this is more easy to control the oxidation. You can also work inside a glow box, and then you can control the oxidation. We are working in ambient lab environment. That's one. The second thing is about the particle size. So your morphology is very much dependent on the particle size. So what's the density of your bridges? When you look at the cross section under a TEM, yeah. So this is dependent on the flow of gas. So the way we are producing it is you have a plasma and you are condensing particles out of it. So what's your flow rate? Because that's the quenching effect, right? So that defines the size of your particle. So we can grow particles which are 5 nanometers, but we can also grow particles which are 30 nanometers, 30. So this is also a factor. Coming to your first question about yield. So we are collecting almost 80% of the particles we are producing. This we do by checking how much particles are in the exhaust of our reactor. We have a condensation particle counter. This is the device which we use. So by taking a brief, a very basic calculation about what is the number of particles you're producing at your source and how many are going into the exhaust, you have more or less a percentage of what is happening. Yeah, so this way we can say that we are collecting 80% of the particles. But this is also dependent on the size of the openings. So if you have a bigger opening size, then you collect more particles. But if there is a smaller opening size, so smaller opening size, I mean like a 1 micron opening, it's not going to collect everything. Yeah, because you're also limited by the fringing fields and other electric effects. So it's really a trade-off between what is your opening size and what is this, what is your throughput of your source. So yeah. I hope that answers the question.
Interesting. How monodispersed are those particles? How well controlled?
We are producing polydispersed particles, so it's a log normal distribution of particles. But there is this thing called it's a cylindrical capacitor. It's called a differential mobility analyzer, which takes in all these different particles, but only gives out like a monodispersed aerosol. So we can also deposit them. But right now we have a standard deviation of 2.1 in our polydispersed log normal distribution of particles.
Could you use this for like aerosol jet printing? Because you mentioned you have an aerosol.
We also, so we don't use it, but there is another group in the Netherlands, in Delft, from Professor Andreas Schmidt-Ott, and they are using aerosol jets. So instead of using to collect only electronically charged particles, they're also collecting dipoles and neutral particles. So you can do that for sure. But most of the particles are charged, so the efficiency is not much effect.
Sorry. Okay, interesting. I guess that brings us right on time for the next talk, unless there's another question, we can.
Thank you.
Entertain another question if anyone has thought of anything in the meantime. If not, well, let's play the last talk. I don't think the speaker's here, so I will just play the video, and then as I said, our schedule is not all the way to the end of the session, so if anyone has any questions for any of the speakers, you can still ask it after that video. All right, so let me open this video.
Toxicity and Carney, associate professor of biomedical.
Oh, hang on. Already started playing. My screen. Okay, so the next and last talk for the session is given by Tzachi Cohen-Carney from Carnegie Mellon University, and the title of the talk is Bioelectronics with Nanocarbons.
I'm Tzachi Cohen-Carney. I'm an associate professor of biomedical engineering and material science engineering. I will tell you today about bioelectronics with nanocarbons, or forming input-output interfaces with excitable cell and tissue using nanocarbons. Input-output. You have the biological entities such as a neuron or cardiomyocyte. They are soft and squishy. They communicate via fluxes of ions or signaling molecules that elicit fluxes of ion response. They form networks in situ, spheroids, organoid, and organs. The solid state end of the interface, such as this handful of allotropes of carbons, we can control their optical electrical properties. We know that they communicate via electrons or holes. We can form them or attain them via different synthetic routes. We can modify their surfaces using different chemistries toward and downstream, let's say, applications. IO from my end is the ability to sense electrical and chemical activity of electroactive cells, cellular assemblies and tissues, or ability to modulate cellular or tissue activity either electrically or chemically. Before we delve deep into this topic, let me tell you about the Cohen-Carney Lab. We are trying to push the limits of the current platform to enable long-term investigation and modulation of cellular electrical activity with high spatial and temporal resolution. We are also developing new types of hybrid nanomaterials for both energy storage and conversion and biosensing. A few examples you can see over here are basically three-dimensional biosensing platforms that we developed to record the electrophysiology of human-based spheroids and organoids. Bioelectronics that is as small as an axon using new types of materials that the lab is developing. And of course, the materials that can be used to modulate the electrophysiology of neurons and hopefully in the future myocytes. And materials that can be used for sensing and energy-related research. First, let me thank my outstanding team. Whatever you'll see in the next few slides is the outcome of their really hard work. The first topic of today is three-dimensional engineered tissues and actually the lack of tools to form IO with them. So how come three-dimensional tissues are important? So there's extensive literature that indicate that cells cultured in 3D exhibit in vivo-like phenomena, such as neurite extension that is extended essentially in 3D versus 2D. The cell shapes do represent in vivo-like topology rather than flat and spread out as they are on a surface. The cells that are cultured in three dimensions have lower mortality and basically have a higher neurons to astrocyte ratio. And cells that are cultured in 3 dimensions have elevated synapses formed. This is just a brain-like tissue. You will find similar results when it comes to muscle, cardiac, and different types of tissues that are cultured in 2 dimensions versus 3 dimensions. If you're interested in more information, feel free to contact me and I will refer you to the relevant papers. Here is our concept of the organ on a chip. This is basically an organ on electronic chip, so we call it organ on e-chip. We are going to create a 3-dimensional sensor array that is pinned to a surface, and upon removal of a sacrificial layer marked by this red rectangle, it will self-roll into a 3-dimensional entity, as you can see over here. We can assemble different types of sensors, such as an active sensors, as field effect transistors based on graphene, or microelectrodes based on metallic electrodes coated with conductive polymers, such as P.PSS. The biggest advantage of our approach is that we shrink wrap sensors around the tissue and monitor the electrophysiology of the tissue from all sides of the circumference of this tissue, essentially. Where when you have an organ on a chip, only the apex of this organ will be interfaced with the bioelectronics, and you have no prior knowledge of the state of a cell that is away from the electrode, essentially. So you're getting information from subsets of cells that are in contact with the sensors, unlike our approach that records from 3 dimensions. As a proof of concept, we use the 3-dimensional assembled microelectrode arrays to record from human cardiac spheroids, so embryonic stem cells derived cardiomyocytes, spheroids. So we mount a single spheroid into our 3-dimensional biosensor array, and we recorded 12 sensors concurrently. This is a calcium movie showing the electrical activity using optical imaging. You can see that the optical imaging gives us a single plane of activity. However, our sensors give a three-dimensional information of the electrophysiology. Here are 12 sensors and calcium signal that was recorded in between the channels over here. And basically, from a single sensor level, you can learn all about all the ion transient or ionic current transients, such as potassium, calcium, and sodium. This is an average of 100 bits, so 100 peaks from channel 4. And the red is the average, the gray is overlay of all the 100 peaks. While acquiring a single channel and learning about single device level is interesting, the more interesting is extracting information from the array of sensors. This is what we've done over here. This is actually a two-dimensional or two-dimensional projection of a three-dimensional isochronal map that we created. The details are given in our manuscript if you are interested. What's unique about this platform is that it can be applied to other organs. In this case, we interfaced the self-rolled biosensor array with the cortical spheroids, and we actually applied the whole pipeline of data acquisition and analysis, including the drug screening, in this case, glutamate, a neurotransmitter, a stimulant essentially, and showed basically that one can affect and record at the same time. So what you'll see over here in this calcium imaging, essentially an increase in the firing rate right now, basically, as you can see. And again, one can do single unit analysis and then firing rate analysis, compare it and correlate it basically to calcium imaging. This is really a unique opportunity to fuse this new tool set for future studies of tissue development, disease progression, drug testing and screening in a human tissue. I'm listing this work that was published around the same time we published our paper out of John Rogers' lab. Again, another idea how to fuse bioelectronics with assembloid of cortical spheroids in this case. In the last several years, we reported our unique technique to generate these nano pipe brush-like structures of out-of-plane grown single-to-fuller graphene flakes from a template of silicon nanowire. Basically, you have a surface of 2 by 2 centimeters that is covered by these fuzzy wires. You can see them all over the place. Here is a zoom in on a single wire, and you can see this fuzziness of single-to-fuller graphene. If you're interested, you're more than welcome to go to these papers and other papers we published on this type of material. I'm not going to cover the whole spectrum of devices or bioelectrical devices for neuronal modulation. They're extensively used in tremor control, depression, and pain control as well. What I want to show you is a different way to modulate the electrical activity. This is again from the input end using light. So first technique is optogenetics, basically expressing ion channel that is sensitive to light. And as you can see, you can modulate the electrophysiology of neurons using pulses of blue light in this case. Biggest drawback or challenge in this type of technique is the need for genetic modifications of the organism. The other techniques are basically infrared laser pulses that can alter the membrane capacitance, and I will speak about it in a couple more slides. Essentially, the barrier of this approach is the low spatial resolution and the high input energy that is needed. In the last few years, there's a surge of interest in using nanomaterials or material science-based approaches to modulate neuronal or cellular activity, not just neurons, cardiomyocytes as well, or muscle cells as well. This is using either photothermal or photoelectrical effect. However, these type of materials, though outstanding achievements were done or shown, are limited in their wavelength, limited in their absorption and photothermal conversion efficiency, and limited in material stability. Here is our approach for remote non-genetic optical modulation of electrophysiology. Basically, we're generating this library of optically tunable materials or optically active materials by controlling the properties of the core made out of silicon nanowires and a shell made out of graphene flakes. As you can see, we can control the density, size, and chemistry of these flakes. We'll use a single wire attached to, in this case, dorsal root ganglia, shine pulses of laser, and modulate the electrophysiology of these cells. These are the structures that we generated in the lab. You can see that we can change the density and size of the flakes by modulating the time of the process or the temperature of the process as well. Unlike single-layer graphene, our materials are basically opaque, close to black in color. So you can see a 90 minutes growth time will generate close to 97% absorbance, quite the opposite of single-layer graphene. If you shine pulses of laser on these materials, you will generate this temperature increase due to energy conservation. And we can actually generate up to 7 kelvins with 10 milliwatts of laser pulses. The bare silicon nanowire will barely increase in basically less than half Kelvin temperature change. If I'll summarize all these, what you see over here is fuzzy wires, including Maxine. Maxine paper will come out soon in ACS Nano, so I won't show much data about this one. Here's how we modulated DRG electrophysiology using NT3DFG. Basically, what you see over here is DRG with NT3DFG attached to the membrane. We patch the cell using glass capillary. This is the ground truth measurement. And as we fix the pulse duration and increase the pulse power, you can see that gradually you get close to the threshold, and then you have this all-and-on phenomenon that is the action potential. The whole process is due to the optocapacity effect. Basically, rapid temperature change will change the cell membrane, which will result in a transient current. And once this transient current hit the threshold, you'll have this all-and-on behavior, the action potential. As a proof of this idea, we held the membrane potential in high values, as in negative minus 150 millivolts, and shine the laser, and you can see these transient currents, essentially. If you compare our materials, basically NT3DFG and Maxine, again, this will be published in the next few weeks, you can see that our needed energy to get an effect is a lot lower than the rest of the materials that are being used. This is highly reproducible stimulation when you use NT3DFG. This is just 15 consecutive pulses with the ground truth of electrical stimulation and photothermal followed up afterwards. We can drive a neuron in different frequencies, 1 Hertz, 10 Hertz, and 20 Hertz, as you can see over here. As a teaser, we use now Maxine flakes, which is actually better than fuzzy graphene when it comes to film. And you'll see more of these coming up in the next few weeks in ACS Nano. Another unique aspect of out-of-plane grown graphene is the fact that we can generate these microelectrodes and now use these microelectrodes with the known optical properties of this material to optoporate cells. Using ultra-fast pulses of laser, we were able to demonstrate a transition from extracellular field potentials to intracellular field potentials, and also perform multiple patches up to 9 cells at the same time. It takes few seconds to do it rather than many hours using a patch clamp system, and of course execute drug assays, as you can see. I would like to thank my group, my collaborators, and funding agencies. Thank you for listening.
All right. Thank you for this talk. Well, thank you if the speaker was here, I guess. So that concludes our session. I'd like to thank all the speakers. Are there any more questions? Does anyone have any question? If you do, you can raise your hand or write in the chat. All right. Doesn't look like that. Any questions? Then let's conclude the session, and I'd like to thank all the speakers again, and enjoy the rest of the conference. Bye.